Hello everyone. Today we will talk about energy in the electrostatic field. Let me see if I can move that. Oh, okay. So we're going to talk about energy in the electrostatic field. Right. So we're going to introduce we are going to relate energy, the concept of energy, to the E field, to the electrical field. How can we coherently introduce the concept of energy, and what role does the concept of energy play in the electrostatic field? We already introduced it a bit when we talked about representing the electrostatic field as a scalar field, as a potential field, right? And the electrostatic potential is essentially has units of energy per charge, joules per coulomb, right? So that's what the electrostatic potential is. It has units of volt, and volt is joules per coulomb. It's energy per unit charge, right? So that's one way to look at the electrostatic field as a scalar energy field through the potential energy. So notice I'm emphasizing that this is one of the ways that we look at the field. So this is one picture that I want you to contemplate always when you're thinking about the field. The electrostatic field is a physical thing. It's a physical entity that exists in all of space. So if I draw my traditional three-dimensional axis, the XYZ that represent three-dimensional space, and I imagine that the field is distributed around space. So at every point in space, there is an electrostatic field. It's something that's distributed. It's not a particle that only exists at one point. It exists everywhere in space, right? And then there are different ways we represent. So those are now different ways to represent that field. And the earliest way we represented that field is by using the electric field intensity vector. Right? So let's say this is the position vector that goes from the origin to the point in space. So the electrostatic field intensity vector is a function of position, right? But then we also said we could represent the so that's one way of measuring the existence of the field. We could put a test charge and test for the force that that test charge feels, and that will give us the that will give us a measure of the electrostatic field. Another way is to imagine that there's dipole densities, polarization that's occurring in every point in space, and the field is just measured by the amount of polarization that occurs, the dipoles that are distributed around space, stretch and orient and all of that. So that's the D vector, right? D at every point of R, and D and E are related by epsilon, permittivity, right? And then we also said that we could represent the E field. Instead of representing it as a vector field, we could also represent it as a scalar field, and that scalar field is a field that's distributed over all of space, and it's called the voltage field or the electrostatic potential. Essentially, the voltage picture of the field is as follows. We imagine that we have some charge at infinity, some test charge at infinity, so it exists away from the origin, an infinite distance away, and then we bring this test charge to some point, right? The amount of energy needed, the amount of work that you have to do to bring that charge to that point, let's say to bring it to this P2, for example, or let's say we could bring it to this P, right? So the amount of work that is needed, the amount of energy that needs to be expended by an outside system to bring that charge to that point is also a measure of the electric field, right? If there is no electric field and nothing that's affecting this test charge, we will not need to apply any energy to or any work to get to that point, right? So that I could envision V, I could claim that V is also another way of measuring the same thing, which is the electric field intensity. And we found out that E equals, turns out to be minus the gradient of V, minus the gradient of V, yeah. Okay, and we can do that. We can do that with the electrostatic field, meaning that for the electrostatic field, we can, instead of using E, we can, which is a vector, which sometimes could be difficult to deal. It's sometimes difficult to deal with a vector in three-dimensional space. We can utilize a scalar field instead of utilizing a three-dimensional vector field, only because for electrostatics, the curl of E is 0. If the curl of E was not 0, then we wouldn't have been able to find some scalar field V that we can use to represent the electric field intensity. The point that I'm trying to make is that V, E, and D are really different things, to different probes into the same phenomena, right? And V in particular is interesting because it is energy. It is energy per unit coulomb. So it suggests that the field itself is something that carries energy, right? Because and this is something that we have to be aware of, is that we're claiming that the electrostatic field is a physical thing. It's not some fictitious mathematical entity that we're just assuming. I mean, it is something that exists in nature, and because it's a physical thing, we need to be aware that it carries energy, and the theory, whatever theory we assume about it, needs to clearly show that that entity, this field, should carry energy. If we develop some theory about it and it turns out it's something that does not carry energy, then something would have been wrong. But that wasn't the case. People quickly recognized that the electrostatic field carries energy. More amazingly, I mean, and perhaps we will not cover this in this course. Perhaps you will study this in the next course. Part 2 of this course is one amazing result is that the electromagnetic field in general not only carries energy, it also carries momentum. So the field at every point in space could carry its own momentum, which is something amazing if you think about it, because we're used to thinking of momentum as something that is relevant only for objects that have mass. So it's kind of like tricky to think how something as nebulous as the electromagnetic field could also carry momentum. So, but I'll leave that for now. I'll focus on the energy for now. Okay. So yeah, so we said that E can be represented as a gradient, right? And we said because of that, right, I can yeah, I can define the voltage between points. Let's say this is from point A to point B. So the energy per unit charge, the work per unit charge that needs to be done to move a charge from point A to point B is just the voltage difference between those 2 points, right? So this is the work that we need to do to move the test charge, unit test charge, from point A to point B. Well, any charge really, divided by the amount of that charge, right? So that equals minus integral AB E dot dl, right? we've derived this, we've shown this because so we know that work is just force times distance, and see, I have the Q here. Q came from here, right? So originally I had Q here, so Q times E is force. So remember we said the force, the Coulomb force, is just Q times E. I sometimes write it small q times E. So that's where the Q comes in. So this is the typical formula of the voltage, right? And then this can be written as VB minus VA. This can be written as just the difference between in the scalar field between points B and points A. The reason we can write that is because we know that E equals minus gradient V dot dl, right? And I know from the fundamental theorem as it applies to line integrals, this is the delta is like the derivative. So this is like imagining I'm taking the antiderivative of E, which becomes V, right? So using that fact, I can write this as V B, or let me write it this way to make it more clearer, to tie it closely to the fundamental theorem of calculus. I can write it as VB minus VA. Okay, so this is a bit of a summary, but I just want to show you that the idea, we've already studied the idea that we can represent the electrostatic field as an energy field, right, through the potential energy. Right, so it's a potential energy is a scalar field that represents the electrostatic field over all of space, and it represents it through the amount of energy needed, amount of work needed to reach every point in space. So, and it's a field that has units of joules per coulomb. So we already have that concept that the field itself carries energy, right? Oh, by the way, the negative sign here means that positive work is done only if the external system is acting against the electrostatic field. If there's some charge and it's moving with the electrostatic field, meaning it's moving at the same direction as the field, meaning the field is moving it, then this system is losing energy, so the work will be negative. Similar to if you have a boulder and you let it fall on a cliff, on an incline, it's the whole system is losing energy. But if you push it up the incline, the system is gaining energy. So the key relationship here is that the work or the energy is just the charge. You know, I prefer to use small q for those things, right? Times the voltage. Right? So if I move a charge from point A to point B, the key insight from the voltage is that the work needed to move the charge from point A to point B is just Q times the voltage. So here I applied some work. So I applied some work to move the charge. That means the whole system gained this amount of work. They gained this amount of energy. Right? Similar, when I push a boulder uphill, the whole system, including the boulder, gains energy. So the point that I want to make here is that where does this energy go? The key concept here is that this energy gets stored in the field. This energy now exists in the electric field. Right? It's because when I move this charge, I change the electric field in the environment, and that's where the energy went. The energy, I'm claiming that the energy went into the electric field. Kind of like when I compress a spring, the energy went into the coils of the spring. So you could imagine the electric field to be kind of like the coil. Right? So energy is stored in the electric field. This is what we are proclaiming, and and we just need to justify it, and we need to quantify it, right? Another way of seeing it, hey, I have some positive charge, and I have a field around the positive charge, and then I have some faraway positive charge, and then I'm moving. I'm an external actor, right? So I'm working on this charge and I'm moving it towards this other charge. What happens if I move it and I keep moving it until it gets very close to this other charge, like this is Q and this is Q, right? If I expend a lot of work to get this very close to this other charge, I will end up with a situation where I have 2Q. So let's say I got this Q very close, such that for me, from my perspective, it appears to be some charge with 2Q, right? So that doubles the field, right? So after I'm done with this action, moving this extra charge, I doubled the electric field around this new charge now, right? So, I mean, it intuitively it makes sense that this field doubled because I added the extra work. So intuitively, it makes sense that to say that the work that I've done, the energy that I've put into the system, the electrostatic system, manifested itself in the increased electrostatic field. Therefore, the electrostatic field is where the energy is being stored. Right? And that's why if I have an electrostatic field of 0, what does it mean? That means that there's no charges anywhere, so or all charges that are at infinity. So I'm assume that I have a boundary at infinity, and all the charges are beyond infinity. Right? In that case, the total field inside the universe will be 0, right? And clearly, such a situation will have no energy. So E equals 0 means energy equals 0. Okay, so that's the claim. The claim is that the energy is stored in the electric field, and it makes sense. And we will show why it makes sense. The energy is not stored in the charge. Right? So the charge is something different. The charge is the source of the electric field, electrostatic field, but it's not where the energy is stored. The energy itself is stored in the electrostatic field. How do we quantify that? Okay, so we want to put numbers into that. We want to put equations to describe that. To show I'm making this claim, and I want to put equations to justify that claim. And there are two approaches. So we could either look at the charges. So we could either approach the problem of energy from the perspective of charges. That's one way to approach it. And then we could approach the problem of energy, the quantification of energy, or the equations for energy from the perspective of the fields themselves. Okay, the field. And both approaches should give us the same results if we have a consistent theory. Okay, and they do. I mean, it will be a bummer if we're teaching you this course and turns out the theory is not consistent, but we do have a consistent theory. Okay, so let's start the argument. Okay, assume this is the all of space. Like this is a boundary of a sphere, represents all of space, and then this is the boundary is at R. This is some origin, right? O, and then R is infinity, right? So assuming we start with all of space that is empty. If there is any charges, those charges exist beyond infinity. So nothing exists within the universe. And then we talked that we want to use the if we do use the perspective of voltage to represent the field, we know that V at infinity is 0, right? That's typically, remember we said that for voltages, all that matters is the difference in the voltage between 2 points. We can take a voltage and we can add a constant to it and it wouldn't matter, right? We can see this from the definition, right? It's minus grad V, and if I take minus grad V plus K is a constant, grad K is 0, right? So it'll be the same. Nothing will change. I could take my voltage and I add a constant to it everywhere. Nothing could change. So I could always, even if the voltage at infinity for some problems is not 0, I can always add a constant to it to make it 0. That's fine. I can always assume the voltage at infinity to be 0. Okay. What happens if I bring some charge Q from beyond infinity and bring it into the space to some point P1? So this is Q1. So this is a charge that I moved from somewhere beyond infinity and I got it into my space. How much energy did I need to do that? Right? I mean, I have to be some big fellow. I mean, if I'm gonna go to infinity and bring a charge, but this is like a thought experiment, right? This is not literal. So how much is the work required to do that? Is anything, there's no field. Initially E everywhere is 0. So there is no electrostatic field to oppose the movement of this charge, right? So I can freely move this charge, right? No energy is required. There's no opposing force that will prevent me from freely moving this charge. So the amount of work, energy needed to move this charge to this point, P1, is 0. Okay, so that's step 1. Okay, step 2. And let me do step 2 in red. I want to take now another charge from infinity. I'm going to move it to some other point, P2. And this is Q2. Okay. How much energy do I need to move this other charge? Well, right now the situation is different, right? E is no longer 0, right? Because I moved the original charge into space, Q1. This new charge, Q2, is going to be opposed by the field that's emanating from Q1. Right? What is the field emanating from Q1? E1, right, is let me forget the origin here. So I'm gonna do r hat, where I mean by r hat is the vector that comes from. I'm assuming now the Q1 is the origin, right? But the form of the electrostatic field is gonna be Q1. We derived this before, right? Over 4 pi epsilon O. I'm going to assume that the material has permittivity of epsilon. So it's general. It doesn't have to be epsilon naught. Okay? R squared. Volts per meter. Okay? So that's the field emanating from Q1. Depends on how far we are from Q1. Okay, so what is, and we can, I mean, we don't have to, we can also derive the voltage, right? So the voltage, let's use the voltage. The voltage is easier. So the voltage, what's the voltage what's the voltage at, oh yeah, we said that the energy can be represented by the voltage, difference in the voltage from infinity to P2, right? That's the voltage. The voltage, how does energy relate to the voltage? Well, we said energy is just the voltage times Q. Right? So I want to calculate the voltage. I want to calculate how much energy did it take me to move this Q2 charge to P2. So I want to calculate what the voltage change was from infinity to P2. Now that there is a source of voltage, which is Q1. So I do the integration from infinity to P2 of E dl, and that's where I use E. So this is E1. This is where I use this E1 that I calculated. Right, so this gives me minus from infinity to P2 of R Q1 over 4 pi R squared dot R hat dr. That gives me, right, so this is V at P2. So this gives me Q1 over 4 pi epsilon. Right, so this goes with this, it becomes 1. What's the integral of minus 1 over R squared dr? That's going to be 1 over R, right? From P2, from infinity to P2. So 1 over R at infinity is 0, right? 1 over infinity is 0. Right? And point P2, what is R there for point P2? So the reference is P1, right? So the distance is this distance, R1, 2. So R is R1, 2. So I have R1, 2, which makes sense. I mean, volts. Anyway, we derived the expression for voltage already previously. So we didn't need to do this integration, but I just did it for completion. Right? But the voltage at P2 is going to be Q1 over 4 pi epsilon times the distance between Q1 and that point P2. Okay? That's how the voltage looks like. And we said the energy, now W2, is just the voltage at that point, right? The voltage from infinity to that point times the amount of charge, which is Q2. So this is Q2 VP2. Right? So W2 is what? Q2 Q1 over 4 pi epsilon R1 2. So remember, now Y1 was 0, the W1 was 0, W2 now is this quantity. Okay. So you see, notice the progression that's happening there. Okay, let's go further now. We want to go to step 3. Okay, so I want to show you a pattern. Okay, so now what's step 3? Let me do now, go to green. This again, this is our universe. Right, and then we already placed 2 charges, one at P1, Q1 at P1, and then Q2 at P2. Now I want to take a third charge, Q3, move it from infinity, this is R equals infinity, to some point P3. So this is Q3. I'm moving some charge Q3 from infinity to Q3. But now this charge is being opposed by 2 charges instead of 1 charges. Yeah. So here I don't have to redo the voltage. I mean, I know what the voltage is at point 3. VP3 is, I know I can use superposition, right? I can calculate the voltage due to P1 and then the voltage due to P2, and I use those 2 distances, right? And I can apply superposition, right? So the voltage at P3 should be Q1 over 4 pi epsilon R13, the distance between point 1 and point 3, plus Q2 over 4 pi epsilon R23, the distance between point 2 and point 3. So now what's W3? The energy needed to move this third charge into points P3. Well, it's Q3 VP3, right? It's the charge times the voltage, right? So that gives me Q3 Q1 over 4 pi epsilon R13 plus Q3 times Q2 over 4 pi epsilon R23. Okay. So you notice how now we have two terms. So we can continue this. So we found W1 equals 0, we found W2 equals something, and then we found W3. We could continue this and find W4, and we'll get 3 terms, and W5, and we'll get 4 terms. So there's a pattern emerging, right? But let's stop at 3, just to detect what this pattern is, right? So if we stop at 3, the total energy of the system will be equal to the total amount of work needed to build that system. And the total energy will just be W1 plus W2 plus W3, right? W1 is 0, W2, let me get it here, Q2 Q1 over 4 pi epsilon R1 2, so Q2 Q1 over 4 pi epsilon R1 2, that's W2, and then W3 is Q3 over Q1 over 4 pi epsilon R13 plus Q3 times Q2 over 4 pi epsilon R23. Okay, so this is the total amount of work needing to build that system of 3 charges. Therefore, this is the amount of energy, logically, I mean the amount of work you use to build the system gets stored in the system. So logically, this is the amount of energy stored in this 3 charge system. Right? Okay, now comes the conceptual point. We started with Q1 and then moved Q1, and then we moved Q2, and then we moved Q3. But notice, in terms of the energy in the system, does it really matter? All that matters is the configuration of the system. Does it really matter if we start with Q1 and then go to Q2 and then go to Q3? It doesn't matter, right? We could have moved Q2 first and then moved Q1 and then moved Q3. We could have moved Q3 first and then moved Q2 and then moved Q1. As long as we end up at the same points at the end, it should not matter, right? It should not matter, right? So I should get the same W. So I should get the same W, even if I started with Q3 and then moved to Q1 and then moved to Q2 and then moved to Q1. All right. So what does that mean? What happens if I do that? I mean, if I start with Q3, that means I need to go to this equation, and everywhere where I have Q1, I just substitute Q3. Because Q2 now is the actual second one, Q2 remains the same. Because Q1 now is the third charge, I go to this equation, and everywhere I see Q3, I just put in, right, Q1. So all I need to do is I need to take this equation and swap 3 for 1. Instead of 3, put 1. Instead of 1, put 3. And I will get the same exact value for the energy, because I did not change anything. I only changed the order in which I'm bringing the charges into their fixed points within the universe. Right? So let me do that again. Let me do W again. So if I do that, I get 0. So remember, I said Q2 is still the second charge that moves. So Q stays the same. But I said I start with 3 and then end with 1. So I swap 3 and 1. So this is Q2. Instead of Q1, now I have Q3 over 4 pi epsilon. Instead of R12, I have R32. Right? Let me start with the smaller first, 2, 3, smaller number. Same thing. R32 is the same as R32. Okay. Now plus, instead of Q3, I put in Q1. Instead of Q1, I put in Q3 over 4 pi epsilon R13. 3 swaps with 1, I get the same thing, R13. Okay. Plus Q3, instead of Q3, I put Q1. Q2 remains the same, 4 pi epsilon R2. Instead of 2, I put 2, and then instead of 3, I put 1. So R1, 2. Okay, this is the same amount of energy. I'll show you soon why I did that. I did that now because now I want to sum those two. So I want to take W plus W, which is 2W, right? So if I take 2W, what I can do is I can also sum those terms together, but I'm going to arrange them in a suggestive way. Okay, so I'm going to take all the terms that have Q1. What terms have Q1? Those two terms. Right? So notice the suggestive way. So I can take Q1 out, and then I end up with Q1, Q3 over 4 pi epsilon R13 plus Q2 over 4 pi epsilon R12. So I took those two terms. And then I want to take two terms with Q2 in it, right? So I'm going to take this Q2 term that starts with Q2, and then this Q2 term. And this gives me also a very suggestive term, which is the following. Q2 times Q3 over 4 pi epsilon R23 plus that term here, which is Q1 over 4 pi epsilon R12. Right? And then I take the final two terms, which are those two terms. I take Q3 out. So I end up with Q2 over 4 pi epsilon R23 plus, what's the second term? Oh, this term, yeah, Q1 plus over 4 pi epsilon R13. Okay, what is this? Notice that this term, what does this look like? This looks like a voltage equation, right? So this is looks like the voltage due to Q3, and the distance here is between 1 and 3, right? So this looks like the voltage due to Q3 at the point where Q1 exists, right? And this looks like the voltage due to Q2 at the point where Q1 exists. So this looks like a superposition of the voltages that, from the two charges other than Q1 at the point where Q1 exists. So this looks like the voltage at Q1, right? So this is V1. This is the superposition formula for the voltage at Q1 due to Q2 and Q3. In the same manner, this is the superposition formula for the voltage at Q2 due to Q3 and Q1, and this is the superposition formula due to the voltage at Q3 due to Q2 and Q1. So, and there's a 2 here that I can take to the other side, so I end up with this expression now for the total amount of energy, which is way simpler than the expressions I had before, which is half times Q1 V1 plus Q2 V2 plus Q3 V3. Right? This is the total energy that's put into the system. If I get three charges and I place them at a certain positions in space, right, the energy is just half times Q1 times the voltage at Q1 due to Q2 and Q3, right? And then plus a half Q2 times the voltage at Q2 due to Q1 and Q3, right? Plus half the charge Q3 times the voltage at Q3 due to Q1 and Q2. So this shows me a pattern. Okay, I did this only for three charges, but there's no reason. I mean, this pattern clearly is going to copy itself, and it's not dependent on the number of charges. This pattern is going to repeat itself, no matter how many charges I move in. So I end up with the equation for the energy as being energy that I stored into the system by moving the charges from infinity to their respective points in space. I end up with this equation: half I equals 1 to n. Let's say I have n charges, right? Qi Vi, and this is the energy equation as a function of the charges, joules, as dependent on the charges. Okay. So this is one way of calculating the energy inherent in that's stored in an electrostatic system. And we used it based on an argument on moving charges from infinity to space, right? To certain points in space. Right. Later, we will derive that same energy from the perspective of the field, and both should match. Right. By the way, in terms of in the field of electrostatics, joules, 1 joule of energy in an electrostatic system is a large amount of energy. Typically, people use smaller amounts, smaller units for energy. One famous small unit is the electron volt. So this is an alternate smaller unit of energy. You would see it in publications or research on accelerators, right? So essentially, 1 electron is a volt of energy is the energy needed to move an electron. So this is an electron, the thing that spins around the atom in a hydrogen atom, right? Moving it from infinity to a point where the voltage at the point equals 1 volt. So moving an electron from infinity to a point where the voltage is 1 volt, that energy expended in doing that is equal to 1 electron volt. Right? So we said W in this case is going to be, yeah. So what's that energy, by the way? What's 1 electron volt? Right. Well, I mean, it's so we said the energy for moving one is so we know that V is voltage is just energy over charge, right? So if I have energy, I multiply it by charge, right, to get voltage. So 1.6 times 10 to the minus 19 coulomb, that's the charge of the electron, QE, right, times 1 volt. 1 volt is like 1 joule per coulomb. That gives me the amount of energy that's in 1 electron volts. So that is 1.6 times 10 to the minus 19 joule. That's what 1 electron volt is. So it's a very small quantity of energy. And this is more, you'll see it more, much more used in atomic physics or in particle physics instead of joules. Joules is a humongous unit. Okay, so this is this formula. We could write this formula. Let's say we have a system where we don't know the charges at certain points in space, but we know the capacitances. So we know C1, C2, C3. So we know like we have a bunch of objects, and we know the capacitance from that object to infinity, let's say. Right? So we could write the energy in terms of the capacitance too. Right? How do we rewrite this equation in terms of the capacitance? We know the formula, right? So energy is half I equals 1 to n Qi Vi. I know that Ci is always going to be Qi over Vi, right? That's the equation for the capacitance, right? So I can write W. So instead of Q, I could put Ci Vi, so I end up with half I equals 1 to n Ci Vi squared. So in a situation where I have a bunch of objects and I know their capacitances with respect to infinity, and I know their voltages, I can use that to calculate the energy in the system using this equation. Let's say I don't know the voltages, but I know the charges at each object, right? Q1, Q2, Q3, Q4. I know the charges of each object, and I know the capacitance of each object with respect to infinity, but I don't know the voltage at each object. I can also use this formula, so I can say that Vi equals Qi over Ci, and I can plug that in. I get half I equals 1 to n. Instead of Vi, I get Qi squared over Ci squared. So I end up with Qi squared over Ci. So those are three different ways of calculating the total energy of the system. Okay, those work for discrete charges, right? So let's say I have this space, right, and this is r equals infinity, and I have discrete bunch of charges. So if I have 100 charges, I can use this formula to calculate the energy in the system. What if I have a charge distribution? Like I have just a charge distribution. I have rho v. Okay, I mean same thing, but now instead of summation, we do integration, right? So now each small volume. So this is dv prime is going to have a charge of rho v dv prime, right? So I should get the same exact formula as this. So it's going to be half a sum of Qi Vi, but now I'm going to have an infinite amount of charges, but each charge is going to have an amount of rho v dv, which is an infinitesimal amount. So the actual summation, this summation turns into an integration. So the formula for the energy is going to be now half, and instead of the summation, I have now a volume integral over the whole volume. This is V prime, right, of rho V dV prime. Rho V dV prime gives me the charge times the voltage at the point. Okay, this is now the energy. It is the same thing, but now because we have an infinite amount of infinitesimal charges that we have to move each from infinity to their respective location in the charge density, we get the same result, only the summation turns into an integration. And then we can repeat that for surface densities or for line charge densities. Same thing, but now with surface charge densities, the triple integral turns into a surface integral. So let's say, yeah, I have my space, and then my configuration is a surface charge density or a line charge density. So it's the same thing. It's going to be half, and the summation turns into a surface integral s prime rho s v ds prime, where s prime is the surface, and this line is going to be L prime, right? And the energy now in the line is going to be same thing, half integral over the line rho L V, the voltage, across the line as we're moving across the line. Okay. So this is one way of calculating the energy in the electrostatic system, through the charges, through imagining that we moved the charges from infinity to their current configuration. And we said that energy is stored in the electrostatic field that arises, because, I mean, previously in space there was no electric field was zero. We expended a bunch of energy to bring charges in and place them in certain locations. So this is energy we fed into the system. Due to feeding that energy into the system, now an electrostatic field is established, Therefore, this electrostatic field is where that energy got stored. If we release the system and we allow the charges to move freely and disperse, perhaps go back to infinity, roll down the hill, right? Then all that energy is gonna be dispersed, and the evidence that this energy was dispersed is that the E field where the energy was stored goes back to zero. Okay. In the next lecture, we want to go through how to derive the equations for the energy based on the field variables themselves, E and D, instead of depending on the charges. Okay, so this is also an very interesting calculation that hammers in that the energy is in the field. The electrostatic field is actually an energy field. It's an energy density in space. Okay, so we're gonna go into that calculation next lecture. Okay, thank you.